Binary search tree. See, this is very important. Binary. Why we are studying trees? This is the reason. Binary search trees. Because whatever, why, whenever we do, we need to store the data, right? We store the data in form of binary search tree. Why it is important? Because whenever the data is sorted, right, it's easier to find
Yeah.
and quickly we can find. And that's our main idea. We need to reduce the time to our search things so that we can quickly calculate the find our resources. Yeah. So let's try to understand what is the difference between a simple tree and a binary search tree. Just let's
Okay.
say.
Okay.
hmm, Maybe this is our tree, let's say. Yeah. See, the binary search tree have a simple idea. This is how you can say a root. So whatever it is in the left subtree will be less than this root, and whatever is in the right subtree would be greater than this the root. Let's suppose I'm talking about now the value. Now values are very important, the data. So this is the one. So this cannot be greater than one. It will have to be zero or minus one if you can take. It can be two. Then it applies to every root node. So if it is two here it should be greater than this, but it should be less than this. So maybe you can use at max you can use two. It's fine. Equal to sometimes it's not a strict definition. It can be equal as well, but it should not be greater than it. Okay. So let's say two is there, you
Yeah.
can make it three, and here also it should not be greater than this. You can make it one. That is fine, but it should not be smaller, greater than this. Yeah, this is a binary search. PST, you can say that. What it means, simple. Simple it is. Whenever you are at any node, if you go to the left subtree, this is a subtree. We not talk about subtree. This is a complete subtree. What is a
Okay.
subtree? The left child treated as a node, treated left or right child treated as a node, treated as a root node, the tree from there, root node, the tree from that node is known as
Okay.
subtree. Okay, so this is something I will frequently use subtree. So subtree is like suppose this is our one more node. So this is our for this no- for this node this is a complete this is a subtree left subtree and this is a right subtree. Okay, now this node for this node, this is the left subtree, nothing on the right subtree. This is how it works. This is the left subtree and right subtree. Yeah. So binary search tree, I told you, whenever you are any node, you just take the left subtree. It should follow the same property that whatever all the nodes in the left subtree, they should be smaller than this root node. And whatever are the right subtree, it should be larger than the our root node. Okay. Now,
Yep.
how it helps and how it helps us, let's try to understand. So, do you know something known as binary search?
Yes.
So basically, what we do, just a quick recap. Let's try to write the code for binary search as well. What we do, let's say we have a sorted array, one, two, three, maybe four, five, nine, 10. We have a sorted array. What we do, what we have to search the element in this array. So how will we search it? One trivial way is to iterate completely and search the element whatever you want. The other
Okay.
efficient way is to divide this array into two parts. So what we will do, we will divide this array into two parts and the partition will be at the midpoint. So let's say the midpoint is this. Since the elements are odd, there should be one element, right? So yeah, we divide the partition 1, 2, 3, 4. This 5, 9, 10. and we'll ask him, the mid guy could be this. So I will ask him, let's say I want to search for 9. Oh, can you tell me, uh, is the mid element is greater? I will make decisions on the basis of mid element is greater than my key, equal to my key, or less than my key. These are the three possibilities, right? It could be greater, it could be lesser, and it could be equal. Key is what I am searching for. What I am searching for. Here it is like key is equals to like searching for. So just there are three possibilities. If this is the possibility, I return it. Oh, I found it. Return found it. But suppose now this is the possibility. Suppose it is greater than key or it is less than key. In our case, it is less than key. My key is 9 and I am at 4. So what I need to? Can my element exist? I don't know this 9 exists or not till now. I am just seeing it, but the computer doesn't know till now, right? So
Yep.
I will say, oh, mid is smaller. That means till low to mid. I can obviously say that your element cannot find in this range. That's the 100% sure because mid is only smaller. The left side elements would be smaller than mid. Then how would your element will found be here? So it cannot be found here. So what we will do? We'll restrict our low and we'll update our low to mid plus one. If our key is less than, oh no, your key is greater than mid element. Key is greater than mid element. Okay. And then we will say, fine. Suppose key is less than mid element. What will happen then? Let's suppose I am searching for 2 and I am at 4. So, okay. So basically, our key has to be in the left side. There's no need to search on the right side. What will do? We'll reduce our high and make it
Okay.
mid minus 1. Means highest to highest. Obviously, mid we already checked. That's what I'm doing mid minus one because mid can't be the answer. Mid we check. If it is, we will check first this. If it is equal, that's our job. We found the key. If it does not happen, we just check for these two conditions. Key is it greater than key or less than key? If it is greater than key is greater than mid, then we will update our loop because the key is bigger and I need to push my range toward the higher side. So how I push it? So basically increasing my low. So basically now my new range becomes low to high here. In the later case, my range becomes low to high. Maybe you can say here. Now will I again this partition do it and do it and do it. And this will help me to search any element whether it is present or not and also at which index in log n time. Because we just do the partitions n by 2 then plus n by 4 and so on. Okay. And by and this is some sub to log n only. So yeah. And by so yeah, this is something you should be aware of. Less than log n, you can say less than log n. You should do that. This is less than log n. So yeah, more precisely we say that this is a log n thing. So yeah, this is a similar idea we will use in the binary search tree. So
Okay.
how
Okay.
will we search in a binary search? This is our question. Search because this is our main concern, right? Search
Yep.
in a binary search tree. Okay.
Uh, can you give me 1 minute? I'm gonna just go to the washroom real quick.
Sure, sure, sure. No problem.
Okay, I'm back.
Okay. Wait. Mm, So there we are. So let's try to write the code for the searching part. Mm, Just a second. Just a second. Oh yeah, good one. You are able to see my screen, right?
Yep.
Okay. So basically, let's try to understand how we can use this similar idea to search in a binary search string. So let's say that let me make a binary tree. So the big three, let this to be one, maybe to be two, and it could be four, it could be maybe two, or it could be two, it could be maybe three, and it could be let's say five. Yeah, but this is my binary search tree. It follows all
Yep.
the properties. In short form, you can say it is a BST. BST, we generally say BST. Okay, let's try to understand how we'll search that. Let's suppose I want to search an element. Let's say I want to search for 4. Whether 4 exists in my binary search tree or not, I need to understand. So now, instead of going with the iterative order, because we know that we need to traverse it, so better to use recursion for that. So we'll use the recursion. So we will maybe you can say return void also. Yeah, you can say a bool thing. Bool, so no, void only we'll say. So yeah, void only. Search. So you can say find. You can better say find. Find. Basically, the root is there. We have to leave the root. One more thing we require this time. The key we need to search. In key as well. We need the key as well. So we got the key. Fine. Now, basically, firstly we'll say if root equals to null.
Yep.
Obviously, return nothing you can find. If root is null, we are not searching for root null, right? So yeah, it's return from here. I don't need that. No, fine. Now when I reach here, I know that my root is not null. So that is I'm sure. Now I need to check. Similar in the case of binary search. I need to check whether my root is equal to my key or not. I will check if root
Okay.
dot data is equals to key. If it is equal, so then to this you can return and making maybe we can make it making return true only. Yeah. So maybe we can make it bool so that we can return it true. Okay.
Yep.
And now there are again two possibilities arises if root dot data is let's say less than key. Now let's try to understand where we need to search. My root data is less than key. That means I need to increase my root's value. So I have two possibilities. Either I go in my left subtree, either I go in my right subtree. But I know that to increase my value because key is much higher. For in this case, this example only, key is higher. I can't go to left. If I go to left subtree, then my value will decrease definitely. It won't increase. So if I want to go, I want to increase the value. I need to go right. So basically, what we'll say, you can say, uh, take a function left and just take the value. Maybe you can return also from here. This is fine. You can say return uh, find root dot left. Root dot right, sorry, because you need to go to right, right? Because our value is small. I need to increase my value. So that's why I need to go to the right subtree. And what else remains? If this is an else if, and similarly, whatever else remains, you just return fine root dot left. Because what is the remaining case? The remaining case is my key is smaller. So basically my key is smaller than my root dot data. I need to reduce my data. So where I need to go? I need to go in the left subtree. So if I want to go to
Okay.
the left subtree, search in the left subtree. Don't search here and there. So that's how we reduced our time from here. So basically this we going to there. So let's try to understand how will it work. Dry run it and then we will see. Let's say dry running. Uh, Test. So let's say
Okay.
I need to search for four, not four, let's say three. I need to search for three. So how will it work? Firstly, not three. Okay, three is already we have. I should be unique actually, but because generally it makes sense to be binary search to be unique because all the nodes should be unique, so it makes more sense. So let's try to make a tree for that case. Let's try to search for five. Okay, so let's try to search for five. So firstly, I'm this node. Right, this node. I will check. I will ask. Oh, are you my key smaller or greater? Oh, you will say your key is greater. So go to right subtree. I reach here. I will ask him now. 4. Oh, tell me, is 5 key greater or lesser? Oh, key is greater. Go to my right subtree. So he go to this right subtree. Fine. So he reaches here and he compares the key with the root's value. Oh, he found it. That's fine. That's great. Jumbo. Now let's try to search for let's say maybe 1. Let's try to search for 1. So I will ask him whether this is smaller or greater. Oh, your key is smaller. You can go to my left subtree. So there you reach and you compare the value. You found it. So let's suppose I make a big example. Maybe 2, maybe 5, maybe 4. But 4, it could not be. Hmm, just make a difference of 1 would be difficult. Let's try to make it 7. Let's try to make it 10. Let's try to make it 8. And let's try to make it maybe 20. Yeah. Now let's try to think if I am trying to maybe 10 should be greater than 10, maybe 15. Yeah. Yeah. Let's try to think if I'm searching for maybe 14, what it will do. Okay. So
Yep.
he will search from start from here. Oh, 14 is so greater. I don't know 14. So go to my right subtree. Okay. We go to the right subtree. That's fine. Then I will ask him, oh, you 14. Oh, 14 is too greater than me. So go to my right subtree. Fine. Go to my right subtree. So now 20. Oh, you reach 20. 22 is greater. 20, your key is smaller than me. Go to my left subtree. Nothing is, you go to 15. Okay. 15 you reach.
Yep.
Now you will ask him, oh, 15. 15 is still greater. Go to my left subtree. Oh, you reach is null. That means the key does not exist. Key does not exist. You can just write on a false and a null. Let's try to write this code as well. We'll understand it better. Hmm, basically, let's try to write void, not void. Let's try to write bool only. Bool. Fine. We just need a node star root and a key as well, obviously. Key. Then we will check if if he ever reaches null, that means the key does not exist. Return.
Okay.
Because he reaches a null, right? And whenever he reaches a null node, that means your key does not exist there. Okay, maybe you can say mm, we did we didn't find key. We uh, key not found. Okay, fine. What if?
My root is same. My root dot data is equals to key. Oh, that's great. Jumbo. Return a true. Fine. Else if root dot data could be less than key. Okay. My root data is less than key. That means I need to increase my value. So I need to search, maybe fine. I need to search in the root dot right. Go on right side, bro. It's very important because I need to increase the value. Find root dot right and also the key I need to send. And then what else is remaining? Nothing is wrong. Maybe not. What happened? What happened? Root dot. Oh, fine. So basically, oh, maybe mistake it. Similarly, I just need to write here. If I this is the last case, my root key is smaller than it's greater than key, so I just need to go the left subtree. Just find in the left subtree root dot left. Oh no, able to do that. Root dot left, and then just find the key. Okay, let's try to see if it is working fine or not. Let me just remove these things. So find. Let's say key root, so we let's say we make this tree 20 with 3, this one 7 2 10 8 20 15, and okay, so let me just find maybe root for obviously I need to give, let's say I need to find 15, let's say 58 I need to find, let's say 8 exists in a 3 or not. So 8,
Yep.
then let's try to print it will print 0 or 1 based on that. So let's try to build this tree as well. Mm, Let me just delete them. I think many of them I just created slab of this. Okay. Let me just initialize the game. Yeah. So I think 7 is the root node. 7 to 10. Okay. 7. Then left one is 2. Nothing on the left. Nothing on the right. It's 10. What is in the left of 10? Left of 10 is 8. So 8. What is left of it? No one. The right of it? No one. What is right of 10? I think it's 20. 20. What is
Yep.
left of? It's 15. Nothing on left. Nothing on right. Nothing on right of 20. Okay, 1 it says. Okay, it finds our node. Let's try to write for, let's say, 14. If you want to search for, let's search for 14. One trivial way, this also, you know that, right? You can traverse the complete tree using in order, pre-order, post-order, and you can just check is root dot data is equal to key or not. That is also a search method, right? But it is not a BST. In a general tree, if you want to search whether a key exists or not, you can use that method as well. But what it will be its time complexity. You need to traverse to each node. What we are here doing today, we're skipping these nodes, right? Let's suppose I'm 7.
Yep.
My key is greater. I am going to right. I'm completely ignoring this subtree. I'm ignoring all these nodes. But whenever if I do a traversal, I go to each and every node and compare. If you can do that as well, but that would be of number of nodes.
No, okay, okay.
Number of nodes. And here, what's the time complexity? Let's try to evaluate. Here, it makes what calls you can make. You can make O of height. Now here
Yep.
comes the twist of height. But you are saying this method is good. This method is good in most of the cases, but when it is not good, let's suppose our tree is like this. This is a skew tree. This is known as a skew tree. Say I make it one,
No.
two, three, four, five, six. This is known as a skew tree. Skew. Skew means like you can say one direction, only one direction it is happening. Maybe two, three is all. So there it can be like this, but yeah, the main idea is this is the uh, situation. One, two, three is it's very linear. So when you will search, right, it's almost you can say you're searching linearly. So this is also a problem in binary search trees that the tree should be a term used as balanced. Balanced.
Yep.
The balance is means the height difference between the left subtree and the right subtree should be at most one. So what it means? So when you go here, here, it should be like this. This is a fine. This is good. Maybe this is also good. You can go this. You can go this. Maybe you can go this. You can go this. This is fine. This is more better than this. At least try to make the height difference as minimum as possible. Make the height difference as minimum as possible. Okay, as possible. Possible. Yeah, more or less, this is the thing. So yeah. So this is the binary search tree, and we have discussed today. Yeah. So basically, what we have, let me just review it quickly for you. What we have discussed
Okay.
today. So today we discuss firstly the height of the tree. So what is the height of the tree? What to understand, we can do it with two methods, either using level order traversal or either using recursion. Level order traversal is very easy to understand, just a minor change in the normal level order traversal. If you know how a level order traversal code works, it is very easy. Other way is recursion. That is a more generalized way. We need to understand that as also because most of the question will be revolved around recursion only in the tree case. So we need to understand how recursion works. So I told you this is the way in level order. And then we
Yep.
saw the code for this one way of the using level order. You just need to increment the level and just we can return the level. Yeah, that also works. Now, the other case we reviewed at the recursion case, how we wrote the recurrence relation, how we go to the left subtree and ask his height, and how we go to the right subtree and ask his height. And when we have both the heights, we just say, oh, please give me the maximum of both of them. And then we will just do it. Just go and get the code for you. So, mm, this is the level of the, this is the code also. Just paste in the notes. Mhm. Basically, this is our code also. So how it's look like recursion thing, recursion. So how we call for the left height, how we call for the right height. We pass the left root dot left and then root dot right. And when we have both these values, now I can tell you the answer. And this is the job of recursion calls. These are recurrence calls, recurrence calls. And then max of left height comma right height plus one, and then you can just return the h from there. And then basically height of the tree, basically we wrote the code for it, basically how to calculate the height. This is node star root. If root equal to null, return zero. Int left is equals to, we just go to the left root, and then we just right, we go to the right root, and then we just calculate the
Yep.
answer from max of left comma right. And yeah, then we talked about something about binary search trees. How, what is the basic definition? Definition is just we talked about that the left subtree, all left subtree values, subtree values should be smaller or equal to or equals to root node root, and similarly all right subtree values, right tree values should be greater, should be greater than, should be greater than equal. So basically, this you need to keep in mind. And then we talked about how binary search works. This is a similar idea we use in the searching part of it. It's searching. So basically, same idea as searching also. Then we just try to find a function. We just check whether the root is null or not. If it is null, you can say return false from here. Basically, oh, we didn't find any node. And then if you just try to, oh, you get the key, that's return true. Now, these is the important cases because these about two are very easy to understand. Oh, root null, or return we have to false. This, oh, we find it, this is true. Now, this is very important when we don't perform out of both of these, it doesn't happen both of them. Then we need to check, oh, root dot data is less than key or not. If it is less than key, that means I need to increase my data because key is larger. So I need to search in the right subtree, you can say right subtree. And then similarly, if not happens in this key is smaller, so we need to search in the left subtree. Just we wrote the code for that. We just understand how it depends. Here in a generality, it depends on the number of nodes. There is no constraint. Here, in case of BSC, it is a
Okay.
general tree in case of this. And then we discuss about a skew tree, what is a balanced tree, how we make when we are making a binary tree, we should make it more balanced so that the searching operation helps. So yeah, today the more or less this is